Hello, this is your instructor, Tom Porepsky, and we're ready for Module 4, which is on probability. First, we might ask the question, well, why probability in a statistics class? Well, if you go back to the very beginning of the course, think about the very basic nature of statistics, where we have to use samples to draw inferences about larger populations. Anytime we do that, there's going to be some chance of an error. What if we have a sample that's not representative, or an extreme sample? How likely is that to happen? So later in the course, there's going to be places where we want to measure probability. Also, if you think about business decisions, businesses make numerous decisions under conditions of uncertainty. What's the likelihood that our sales will continue rising, or what's the chance of a recession in the economy? When you hear words like likelihood or chance or odds, all of these involve the concept of probability. So for that reason, probability is an element of a business statistics class. First, just a definition. A probability is mathematically a number between 0 and 1, or 0% to 100%, that reflects the relative likelihood of an event. This might sound kind of obvious, but believe me, I've had many students give me probabilities such as 2.7 or 3.5 or 15.2, and I have to remind them that those probabilities don't exist anywhere. 0.35, yes. 0.035, yes. 3.5%, yes. But not 3.5. No such creature exists. So be aware of that. If you come up with a probability outside the 0-1 range, and it's not in percentage terms, you've done something incorrect. Higher probabilities, of course, indicate greater likelihood of occurrence. Lower probabilities indicate lower likelihood of occurrence. And at the extremes, the probability of 0 indicates an event cannot occur, whereas a probability of 1 indicates the event is certain to occur. In most situations, however, we're not usually interested in those extreme cases, but occasionally. Now, there's a standard, what I call probability model, that's used in almost all statistics books, whether they be math books, business statistics books, and so on. It's kind of a standard way of going about probability that I call the probability model. We begin with the concept of an experiment. An experiment doesn't have to mean going into the laboratory and doing something. An experiment can be anything that can be repeated over and over and resulting in some outcome. It can be something like rolling a die or flipping a coin, choosing 5 people from the classroom. All of those can be thought of as experiments. The sample space is going to be the set of all possible outcomes in the experiment. And a sample point refers to any one particular outcome. An event is a collection of one or more sample points. And we're usually going to be interested in finding the probability of various kinds of events. One simple way to define the probability of an event is to say it's simply the sum of the probabilities of all the sample points in the event. Now, there are many ways to calculate probabilities. Some of you have already had probability perhaps in math courses earlier in your life. We can use formulas to calculate probabilities. We can use various kinds of tables. We can use what are called tree diagrams and Venn diagrams. In our chapter here, we're not going to have the time to cover all of these ways in depth, but we will take a look at a number of different ways that sometimes help in evaluating the probability of an event. Let's start with what I call the sample point approach to probability, which is a very simple method when it can be used and applied, although it has some limited applications. Define the experiment. Think about the nature of the sample points, and if possible, list them. Just write down the sample points. Now, of course, if you're going to list them, it helps if there's only a small number or not a very large number. We'll see that's one drawback to this approach. Can you assign a probability value to each sample point, making sure that the sum of the probabilities must equal 1? Just like in an earlier module, the sum of the relative frequencies has to equal 1 in statistics. It's true that in the sample space, the sum of all the probabilities has to equal 1. When an experiment is performed, that's just saying that one of the outcomes has to occur. Define the event of interest. What is it you're looking for? What are you trying to solve for? Can you identify which sample points make up that event? If you can, then it's pretty easy to find the probability of the event because you simply sum the probabilities of the sample points that are in the event. Let's do a very simple example. Suppose our experiment is simply to roll an ordinary 6-sided die. Kind of obviously, there's 6 sample points, just the numbers 1, 2, 3, 4, 5, 6. If we wanted to, we could label them like E1, E2 on out to E6. Somewhat logically, if we assume this is a fair, well-balanced die, we'd assume the 6 sample points should be equally likely. Therefore, the probability of any one of them would be 1/6. Get used to this kind of notation. This just means the probability, the capital P here stands for probability. The probability of EI, or that sample point, is equal to 1/6. In this case, it would be very easy to answer any other probability question about this sample space. What's the probability of rolling an odd number? Well, since 3 of the numbers are odd, 1, 3, and 5, each one of those has a probability of a 6th. We simply add a 6th 3 times, and we get 3/6 or a half as the answer. What's the probability of rolling a number greater than 4? Greater than 4 implies 5 or 6, each of which has a probability of a 6th. So the answer is 2/6 or 1/3. Now, that example, of course, was quite simple. We had a nice small sample space. And in that particular case, it seemed pretty obvious to let the 6 outcomes be equally likely. That's not always going to be the case, however. So how do we assign probabilities to those sample points? Well, we have 3 methods. The classical method, which actually is what we just used a minute ago, where we assumed the outcomes were equally likely, the relative frequency or empirical method, and the subjective method. The classical method, as I just said, assumes the outcomes to be equally likely. If I roll a 6-sided die, I should assume the 6 sides are equally likely. If I rolled a 20-sided die, I assume the 20 sides are equally likely. In this case, if you have n possible outcomes, the probability of each one has to be 1 divided by n. And that's what's called the classical approach. I suspect it's called the classical approach because some of the origins of probability go back to gambling games, rolling dice, pulling cards, and many times in gambling games, the outcomes are treated as equally likely. There's a problem, of course, with the classical method. There's going to be situations where the outcomes do not appear to be equally likely. In my classroom classes, I often use a simple example. What if I was going to randomly pick a person from the room, and I ask, what's the probability that I'd choose a female? Should I assume that females and males are equally likely outcomes and therefore have a probability of a half and a half? Well, that would only be the case if the number of males and females in the room was equal, but it might not be. Suppose there were 18 females out of 30 in the room. Well, then I could use the ratio 18 divided by 30, or 0.6, as an estimate of the probability. This is what we call the relative frequency method, or it's sometimes also called the empirical method. This method uses existing data, or past data if necessary, to calculate the relative frequency of an event, and use that as the probability. Let's take a look at an example, and we'll see this relates back to an earlier module where we talked about relative frequencies. Let's say Ace Electronics sells widescreen TVs, and for one particular 70-inch model, we have some sales data here over the past 50 days. Over the past 50 days, they sold between 0 and 3 of these TVs each day. 5 days they sold none of them, 15 they sold 1, 20 they sold 2, and 10 days they sold 3. How can we use this data to assess the probability of selling different numbers of TVs? Well, we can take that data and simply calculate the relative frequencies. 5 divided by 50 is 0.1, 15 divided by 50 is 0.3, and so on. So these become our probabilities, our relative frequencies. 0.1, or in percentage terms, a 10% chance of selling no 70-inch TVs, 30% chance of selling one, etc. Notice again that those relative frequencies have to add up to 1. Finally, in some cases, what if we don't have any past data to go by? In that case, we might have to just begin with a subjective probability based on someone's belief. For example, and again we'll get to an illustration of this later, a firm comes out with a brand new product, and they're interested in the probability or likelihood of this product being successful and profitable in the marketplace. But they have no past data on this particular product to go by. The product has never been introduced before. So they might have to begin with simply a subjective belief. In many cases, you start with a subjective belief, and then you can modify them as data comes available. For example, sometimes a firm comes out with a test market of a new product to see how well it sells, and from that they can modify the probability of success. Okay, if we go back to the sample point approach for a moment that we looked at a little while ago, when we did our roll of the die experiment, we only had 6 outcomes there. So it was pretty easy to count the number of outcomes. In other cases, though, the number of outcomes may not be so obvious. What if we rolled that die 2 times or 3 times? In mathematics, there's a variety of counting rules that can be used to determine the number of outcomes, and we're going to look at a couple of those at various points in the course. Let's do one of the counting rules now. This is called a multiple step counting rule. Sometimes an experiment can be thought of as a series of k steps, where there's n1 outcomes on the first step, n2 on the second step, and so on until you get to nk on the kth step. In this case, the total number of outcomes can be found by multiplying n1 times n2 on out to nk. Let's go back to flipping a coin. Let's say we flip a coin 3 times. How many outcomes are there? If we apply the multiple step counting rule, the first flip has 2 possible outcomes, the second flip has 2, the third flip has 2. 2 times 2 times 2 is 8. So there should be 8 total outcomes. In this case, it's not that hard to write out the entire sample space or use some notation for it. If I let H be heads and T be tails, we have one outcome is all 3 heads. Then I have to write down all the ways of getting 2 heads and 1 tails, all the ways of getting 2 tails and 1 heads, and finally all 3 tails. And if you count there, you have 8 possible outcomes. Another device that sometimes helps you count outcomes in probability is a tree diagram. I start with the first flip. The first flip of the coin is either heads or tails. I have 2 branches to the tree. Given the first flip was heads, the second flip can either be heads or tails. Given the first flip was tails, the second flip can either be heads or tails. And finally, I get to the third flip. Given heads for the first 2 flips, the third one can be heads or tails, and so on. By the time you get to the end here, you're going to have 8 branches to the tree. And those are the 8 outcomes that we just looked at a minute ago. So sometimes, as I said, tree diagrams can be useful in counting the number of outcomes. They can also be used in some cases to help solve probability problems. There are other counting rules. Some of you may have had these in mathematics, permutations and combinations. Combinations will be covered in a future module, so rather than do them here and again later, we will cover them in a future module. And that's the end of the first part, our introduction to probability. And in the next part, we will go further into rules and formulas of probability.